All right, I've got a BJT differential pair drawn here, and there's a few things here. We got to label Q1, Q2. Okay, these are matched, so we could say Q1 and Q2 matched. Okay, and we don't want them to enter saturation. Let's say do not want Q1 and Q2 to enter saturation. Now I believe you covered this last semester. If you recall, for a common emitter transistor circuit, BJT circuit. Okay, so let's look at least for the common emitter configuration. Okay, if you remember, we had again, this is from last semester. You've got VBB here, which is your base voltage. You've got your base biasing voltage. This is the source. It's going to have some source resistance, so we can call that that source resistance value RB. We've got our transistor here. Common emitter means our emitter is attached to ground. Our collector has a collector resistance associated with it, and a VCC. Okay, so again, if you remember, common emitter, you've got collector, base, emitter. Okay, now if we make some plots, and this is what a curve tracer does. Maybe you looked at a curve tracer in the lab. But if we let's just say this: if we plot IC versus VCE, we get a curve. We can actually get a family of curves. And again, I think you may have done this last semester, maybe in lab. I know there is an old curve tracer in the lab. I'm not even sure if it works. But anyways, it's an antique, which most curve tracers I've seen over the years have all been antiques. So anyways, we've got here IC on the vertical axes. We've got VCE. So we've got collector current on the vertical axes. We've got VCE, the difference in voltage between the collector and emitter, on the horizontal axes. And what you end up with these things, let's just change color to a lighter blue here. You get a family of curves that kind of look like this. Remember that? Maybe you do, maybe you don't. Not the best diagram. I'll give you an idea. And we can identify some voltages here. Okay, we can identify a voltage here, 0.7 volts. Okay, that number should be familiar for a silicon transistor. And I'm going to identify another voltage right here. I'm going to call that VCE max. And we've got different books call these regions different things. We've got here between 0 and 0.7 volts, or why don't we just say less than 0.7 volts. Your book calls this the off region. Okay. Then we've got over here greater than VCE max, saturation region. And in between those two, we have what's referred to as the active region. This is where the transistor is acting like a transistor. And each of these curves, I forgot to mention this, each curve is for a different value base current. Okay, and people refer to these as family of curves. So So I think you probably saw this last semester. So let's start a new slide here. If I can figure out how to do that with my new software. Okay. And we can look at the basic operation of this thing. Of a BJT differential pair. So let's apply a common mode voltage ECM to the two input-based terminals. All right, so we go back to our original configuration. I'm just going to draw it quick here. We've got our C, Q1 attached. And we've got another RC over here, Q2 attached. Current I, negative VEE. We got VCC up here again. This is RC, VCC. We've got a common mode voltage. Let's put a polarity in. Minus, we'll call this VCM. And we'll put another one over here. Plus, minus, VCM. Okay. Q1, Q2. Okay, so we got to do a little recall here. There's a few things we want to remember from last semester. Let's say recall from chapter 6, page 310, I think it is. Alpha, okay? Alpha is beta over beta plus 1. Remember beta? Okay, so alpha is a constant close to 1. Okay, and it's the common base current gain. Common base current gain. Okay. If you notice, if you look at this, small changes in alpha correspond to very large changes in beta. So, and I think you can see why. And when you look at this, it's super important the transistors be matched as close as possible. Okay. And again, beta. Let's say what beta is here. Beta. We've used that before. That's the common emitter. Current gain. Okay, so it's really important the transistors in these differential pairs be as closely matched as possible. So we can define, and again, this is stuff you covered last semester, but we can define our currents here. Okay, alpha I over 2 for both of our collector currents. Okay, we can call this just I over 2, our emitter currents. And VCM, if you remember, and I know you do, silicon transistor, we're going to drop 0.7 volts between the base and the emitter. Oops. 0.7 volts here. So Q1 and Q2 both drop in 0.7 volts, base to emitter. So the voltage at each collector, okay, well, let's do this first. What we're going to see here is we're going to see a negative, the voltage at the emitter here, at this point right here in the circuit, this is the emitter for both transistors, if they're matched, is going to be VCM minus 0.7 volts. Okay. Now we can say the voltage at each collector and that's at the collector terminal of the transistor itself. So it's on the way I've got it drawn up here, the lower side of RC. Okay, so it's going to be, I'm going to put a couple of red dots here. I should have made red. So we get a red dot here, we get a red dot here. Okay, so the voltage at each collector, VC, is going to be VCC minus alpha I over 2 times RC. Okay, and the difference, if these are matched between each collector, is going to be 0 volts. Okay, so now that's if VCMs are matched. If we vary VCM, if the VCMs are different, let me add a new page here. Okay, so we can say, let's say this now. If we vary the value of VCM, okay, as long as Q1 and Q2 remain in the active region, and the current source I has enough voltage across it to operate properly, the current will split evenly between Q1 and Q2. Q1 and Q2, and VC will not change for either Q, for either transistor. Okay, so like magic, changes in common mode input voltages are rejected. Okay. Okay, now let's look at an example, and let's talk about some of the things, this concept of current steering we talked about with the MOSFETs. So let's say, now let's look at following. Okay, we've got our same old circuit again. Got RC, Q1, RC, Q2. Got a current source I, we've got negative VEE. We've got VCC up top here. We've got RC, and we've got RC. Okay, let's put 1 volt here on the base of Q1, plus 1 volt. Display explicit. Q1, Q2, attached to ground. So we got plus 1 volt on Q1 on the base, and we've got 0 volts on the base of Q2. All right, so what are we going to have here for values? Okay, basically, well, let's write a couple other notes here, just so we are perfectly clear. VB1 is 1 volt, and VB2 is 0 volts. So Q1 is going to be on, Q2 is off. Okay? And if we want to be a little more, I guess, explicit about that, we can say Q1 base to emitter junction is forward biased, and the Q2 base to emitter junction is reverse biased. Okay, so what are we going to have here? Let's take a look at this. I'm going to define some currents. Okay, all the current's going to go through Q1. So current through Q1 is going to be, at the collector, is going to be alpha times I. Current through Q2 at the collector resistor is going to be 0. All right. So Q1 is forward biased. So we're going to be dropping 0.7 volts here, which is going to leave us with, right here, at the emitter, it's going to be 1 volt. The base voltage for Q1 minus 0.7 volts is equal to 0.3 volts. Okay, so we got 0.3 volts here. Okay, right here. So we've got 0.3 volts plus 0.3 volts at the emitter of each transistor. All right. If we've got 0 volts here, okay, VBE2, if we want to call it that, is going to be what? 0 minus 0 volts minus 0.3 volts is a negative 0.3 volts. Negative 0.3 volts. All right, let's add another page here, and we can say IC1. We already did this. We wrote this on the diagram. Is alpha times I, and IC2 is 0. Okay, so VC1, the voltage right at the collector, right on the collector terminal of Q1, is going to be VCC minus IC1 times RC, and VC2, since we don't have any current going through that collector resistor on Q2, VC2 is just going to be equal to VCC. All right, let's look at a little different condition now. Okay, let's flip it around. Okay, let's say now Q2 is on and Q1 is off. So we can say, if we now look at I'm looking forward to going to the next chapter when we can stop drawing these things. All right. Not that I don't like them. Just getting tired of drawing them. All right. So we've got a VCC here. We've got a... We're going to set up a condition here where we're going to make the base voltage for Q1 a negative 1 volt. Again, that's a negative sign. So this is Q1. It would help if I redo the rest of the thing. Here's I. Negative VEE. Q2. Still grounded, 0 volts. Okay. Let's look at what's going on here now. So we've got RC and RC. Okay. So here, Q2 is on, Q1 off. Okay. Q2. Base to emitter junction is forward biased. Q1, base to emitter junction is reverse biased. Okay, IC2, I should have put some values in here. We're going to have no current going through Q1. We're going to have all the current going through Q2. It's going to be alpha, again, times I. Okay. We've got 0 volts here. We're dropping 0.7 volts here, which means VE2, or VE, I'm sorry, is going to be 0 volts, the voltage at the base of Q2, minus 0.7 volts, so it's going to be a negative 0.7 volts here. Okay, and VBE here is going to be what? On Q1, VBE on Q1 is going to be a negative 1 volt minus the negative 0.7 volts is equal to negative 0.3 volts. Not enough to turn it on. So again, that Q1, base to emitter junction, is going to be reverse biased. So Q1 is off. All right, so where were we here? We can say IC2. I already wrote it up there, but it's alpha times I. And IC1 is 0. VC2 is going to be VCC, because it's on, minus IC2 times RC. And VC1 is just going to be VCC, because no current flows through that collector resistor attached to Q1. So our current can be easily steered from one transistor to another. Okay. Easily steered from, I can spell it right, from one transistor to the other. And this is really, it works really nice for different kinds of circuits. This works really nice for logic circuits, for example, which are covered later in the book, I think in chapter 15. So let's take a look at one more thing, just like we did with the MOSFETs. There's a, if you remember, there's a range, what we call the common mode range. So we want to talk about what that common mode range is. There's a common mode maximum voltage and a common mode minimum voltage. So let's do this here. Let's add another page. So we'll say input common mode range. be the last time we draw one of these things. Okay, so here we go, differential pair. VCC, RC. So we got VCM here. There's our second transistor. Okay, VCC. Another VCM here. We've got our current source here and a negative VEE. I. Okay. We had, let's just put some sort of general designations in here. We've got IC1, collector current for Q1, IC2, collector current for Q2. I forgot to put circles around these, and I forgot to label them Q1, Q2, okay. We defined, or we didn't even define it. Let's just say, we don't have to say we defined it anyways, but we've got a emitter current on Q1, and we've got an emitter current on Q2, okay? And if you recall, I think I've got everything we want to indicate here. Oh, right here, we've got the emitter voltage for Q1 equal to the emitter voltage for Q2. And we can define a couple of, again, our VC1, transistor collector current for Q1, VC2, collector current for Q2. So we can say, recall, we said IC1 was equal to IC2, if they're matched, is equal to alpha, and they're both on, alpha times I over 2, okay? VC1 is equal to VC2, so that's going to be VCC minus alpha times I over 2, which is the current through the collector resistor times the value of the collector resistor, okay? And IE1 is equal to IE2 is equal to I over 2, again, as far as we're concerned, and VE1 is equal to VE2. This is, both of these are on and they're matched. Is equal to VCM is equal to, oops, trying to go too fast here. VE1 is equal to VE2 is equal to VCM minus 0.7 volts if these are silicon diodes. Okay, and if you recall back to that curve we had right at the beginning when we first started talking about this section, we had IC, we had VCE, we had the family of curves, something like this, and we defined 0.7 volts. We said there was a VCE max here. Okay, between those 2 points we said was the active region. Less than 0.7 volts we said was the off region. Greater than VCE max we said that was the saturation region. Okay, and each of those curves, we had a family of curves drawn. I've only drawn one curve here, but each curve we said was for a different value of base current. And again, this is referred to as a family of curves. Okay, the upper end, okay, that's VCE max. Okay, it's determined by upper end of Q1, Q2, leaving the active region and entering saturation. That's a formal definition. Okay, so VCM max, we can say is VCC, I'm sorry, VC plus, I can get my numbers right here, plus 0.4 volts. Again, this is just a formula. So it's, okay, we know VC is VCC minus alpha I over 2 times RC. Again, that's VC plus 0.4 volts. So that's how you calculate that. And again, we're not going through the derivation. The book goes through the derivation. Don't worry about it. Lower end, I want you to just realize there's an upper and lower end of this thing. Okay, there's a VCM min is equal to a negative VEE plus VCS. That's VCS, that's the current source voltage, plus VBE. Okay, and again, this right here is minimum voltage. Cross current source. I to ensure proper operation. And that's it. That's it for this chapter.